My vision. This is 2966 divide array into arrays with max difference. All right. So it's a pretty simple problem. It's a greedy-esque kind of scenario solution. And it shouldn't take us too long to solve it today. So you're given an integer array nums of size n and a positive integer k. All right, so you're provided two things. What are the two things you're provided? Nums and k. Divide the array into one or more arrays of size 3, satisfying the following conditions. Each element of nums should be in exactly one array. So when you see that condition, right, what that's really telling you, kind of simply, is, if you have an array A, B, C, D, E, F, G, well, you're going to divide the array into one or more arrays of size 3 such that each element of nums should be in exactly one array. So you're basically going to partition these things into new arrays of size 3. So this thing should be a multiple of 3, right? And every new array you have will be of size 3, of course, and each element in the initial array will only be seen in once. So you can only use each element once, right? So if I have 9 elements, that means I have to make 9 divided by 3 new arrays. So I'll create these 3 new arrays here, right? And then for each element, I have to decide where I put it, and I can only put it one place, right? So maybe I put A here, I put B here, I put C here, I put D here, I put E here, I put F here, I put H here, G here, I here. I don't know. I'm just kind of arbitrarily choosing here to prove a point, right? So the point is, each element initially only ends up in one new place in the end. And every array is of size 3, okay? So there's really 3 conditions, right? Each array size 3, each element ends up in one array. And the final condition is that the difference between any two elements in one array is less than or equal to k, right? So E minus B, E minus C, C minus B, B minus C, A minus D, right? The difference between them is less than k, right? Return a 2D array containing all the arrays, meaning, so return, this segmentation. If it is impossible to satisfy the condition, return an empty array, right? So why would it be impossible to satisfy the condition? Well, imagine, you had, I don't know, k equals 3, and your array was 1 in 100 and 1,000, right? Well, how are you going to create a subarray of size 3 with these 3 numbers? Because, 1 in 100 are definitely greater than 3 away, 100, 1,000, 1 in 1,000, etc. All right. So we have our first example here. And like I said, it's going to be a very simple problem today. I say that every day because I don't like making video solutions for the complicated problems because they're complicated. 3, 4, 8, 7, 9, 3, 5, 1. 7, 9, 3, 5, 1. All right. And we need to create this new array. So it turns out there is an answer, right? So we have 1, 1, 3. Right, so 1, 1, 3, 3, 4, 5. So there's 2 3s in this array. It's important to think about that. All right, and then so 3, 4, 5, and then 7, 8, 9, right? So the initial order of the array doesn't matter, right? Because we can take elements out and partition them, split them up and segment them however we want. And that point will become important in a moment. But, right, so this works. Why does this work? Well, k equals 2, right? So the difference between 1 and 3 is 2, so it's not greater than 2. The difference between 1 and 1 is 0. The difference between 1 and 3 is 2. 3 and 4 is 2. Oh, it's 1. 4 and 5 is 1. 5 and 3 is 2. 7 and 8 is 1. 8 and 9 is 1. 7 and 9 is 2. So no matter how we partition this, right, it works out just fine. Right, the difference between everything is less than or equal to 2, which is k, so we're good to go. So how are we going to solve this? Well, the first point, right, the first essential point is, well, it doesn't matter how things are ordered, right? And what's really important in this array is, well, each array we make needs to be of size 3, okay? So I guess the best way to do this would be to just walk through and then kind of intuitively gather the greedy solution to this problem, right? Greedy solutions are usually pretty intuitive, and it's based on an observation that forces your hand kind of deal, okay? So when I look at this one, right, what can this 1 be with, right? Well, this 1 can be with anything plus k or minus k away, right? So in order to match with this 1, I have certain elements that 1 can be with, right? It definitely can't be with 8 or 7, but it could be with 1 plus 2, 3, 1 minus 2, negative 1, right? That's the range, right? That's like kind of confined for what 1 could be with. So if I'm looking at all these elements and I'm trying to find candidates for one, I could fish through and I could search through this whole entire array and try to find, okay, who can meet with one? Or just to make it simpler for myself, right? Maybe I should first sort the array, okay? I need to sort this array so that candidates, and when I mean candidates are numbers that can be together, are close to each other, okay? So when I looked at this, I don't know exactly what intuition led me to this. It's something like this, right? Because now I'm kind of doing it in retrospect, right? I'm thinking about what did I think? But when I looked at this, I thought, okay, I should sort it. And why should I sort it? Because I'm trying to find numbers that are close to each other, right? Like I need who can go with one. Well, I'm not going to search through the whole array. If I pre-sort it, I'll know who's next to me. Those would be my best candidates to be with me, right? Right. So this is already kind of the sorted version. So this kind of tells you something about the solution, right? But let's look at 1, 3, 4. So let's sort this array, right? So we have 1, 3, 3, 4, 5, 7, 8, 9, and I forgot a 1. Okay. All right. Now, when we look at our smallest number, right, 1, because we have to split these all into groups of 3, right? So everybody needs to be in their own group. Everyone needs to be in a group of 3. So the best candidates for 1 are the things that are close to it as possible, right? There's no other way to do this, right? This 1 needs to be in a group, and this 1 has to be, compliant with these conditions. So this 1 should be with these 3 together, right? And now since this 1 is forced these 3 into a hand, right? Because now it's forced that min down, right? Like 3 could technically be all over here with 5. This 3 could be with the 5 over here. But since I had to group it with this 1, I no longer can consider that. So then I just ask the same question starting here. I look at 3, 4, 5, and I say, okay, 3. Well, I've already used the previous ones, right? I've already used the things to the left to match with this 1. So who can I be with? Well, I have to be with these next 3. Right? Those are the 3 I have to make it work with. So then for 7, 8, 9, I have to make it work with these next 3. Even though technically, right, I could have like put, this 3 together with this 4, 5, right? But since I've already decided, I had to decide to put this 3 with this 1, it opens up a new space. So that's why this solution is very greedy, right? Because it's like I'm forced to apply this 1 and match it with this 3. So then when I encounter a new 3, now I'm just playing the same game again, right? Now I'm like, okay, now I've had to use these ones to match with this 1. So now with this 3, I'm just playing the same game, right? I'm greedily choosing things to match my solution, right? To match the situation that I'm in. It works. All right, so let's look at a problem where it doesn't work, right? All right, so if I have 1, 3, 3, 2, 7, 3. So 1, 1, 3, 3, 2, 7, 3. So first thing I'll do again is sort it. 2, 3, 3, 3, 7, right? And now when I look at this 1, I'm going to play the same game again, right? I'm going to say, okay, this 1 has to match with the smallest things that come with it, right, to make this work. So I'll put 1, 2, and 3 together. And then I'll look at 3, and I'll say, okay, these next 3 have to match, but they don't match. Why? Because this value and this value, 7 minus 3, is greater than our k value of 3. So that doesn't work. Okay? So really all you have to do is you look at groups of 3, and you just say, all right, I'm going to have to match these 3 together. And since it's already sorted, that just means that in order for everything to be less than k, the largest one minus the smallest one has to be within the boundary of k. And if that works, then okay, I had to put these together, so I'm going to discard them and play the same game with the next group, and the next group of 3, the next group of 3, so on and so forth. So it's just that simple, okay? So what we're going to do is first sort nums, all right? Right, because we want to have it in that form where we can just traverse it through. And then we're going to go in groups of 3, right? So I'm going to go I in range, length of nums. Now it's actually Python, so I'm going to start at 0. I'm going to go to the length of nums. And if you look at the conditions, nums is always a multiple 3, so you don't need to think it's like, oh, what if it's not a multiple 3? What do we do if we have an additional 2 or whatever? Right, so it's always nice when problems have that, little simple condition. And we're going to go in groups of 3s. So what this basically means is I is going to start at 0, then it's going to be at 3, then it's going to be at 6 and 9 and 12 and so on and so forth. All right, and then we're going to say, well, what does it mean if we can't make a group? So the smallest number that I'm looking at, that's nums of I, that's going to be the new group that I'm going to create. In order for it to create a group, this nums of I needs to be less than k than nums of I plus 2. So that means nums of I plus 2, right? Because that's 2 elements away, right? Like when we look at this, right? And then we sort it 1, 3, 3. I always forget that too. 2, 3, 3, 7, right? When I'm basically saying, okay, this is nums of I here, right? And then it's going to be matched with these three. So that means that nums of I plus 1, nums of I plus 2, minus this number needs to be less than k, because that would mean that everything within this range is less than k. Of course, you could, compare. It's only 3 elements, so you could compare all 6, right? You could do, or what would that be? 3 minus 2 divided by 3. So, I could compare this to this, and this to this, and this to this, or something. But, right, if the maximum and the minimum is less than k, then everything in between minus everything in between would also be less than k, right? So, if nums of I plus nums of 2 is greater than k, that means that we can't make this work, right? Because we have to match this I with this I plus 2 because it's greedy solution. We got to just make it work, and that's the best way to make it work. So if it doesn't work then, it's not going to work anywhere else, right? So that doesn't work. Then what is the default condition that we return? We return this blank thing. If we get to the end, so basically if I get through this whole array without having this condition be true, that means that we found that the solution works. So what is the solution that works? We say we return, and we'll just create all those additional arrays, right? So there's nums from I to I plus 3, right? Because it's exclusive range. So this will give you nums of I plus 1, nums of I plus 2, those 3 elements. And then we'll go I in range 0 to the length of nums. It's just the same exact game here. All right. And then we submit that and we cry because I made some stupid mistake as per usual. Okay. Told you. Told you. I told you that would happen. I don't even know what I did wrong. Lifeline. What did I do wrong here, guys? Oh, you have to put if there. Duh. If that's the case, then return. Rookie mistakes. Okay, so what is the time and space complexity of this? So let's say n is the length of nums. Okay. Now for time, well, we have to sort this, so that's going to be O of n log n. And then you gotta look at all n numbers, right? Technically, you look at like n divided by 3, 2 times n divided by 3, because you look at all n divided by 3 numbers, but you look at 2 numbers and make a comparison. But basically, this scales with n, right? You look at all n numbers and you do an operation. So this is, n time, but n log n scales n. So this would just be n log n. And then this, you kind of do this another n operations, right? And then for space, well, it's a little bit complicated because, well, additional space, well, you have to create this array, which is, a segmented version of the initial array. So you're going to create n space in order to return, a new array of size n, a new array of arrays, right? And then this could take n space to sort. There's also constant sorting algorithms, right, with n log n time complexity, like in place heap sort. I'm not really sure what Python does behind the scenes. In an interview, you can just say, well, this may not be n log n, or this may not be n space, but there are constant space. This may not be constant space, but there are constant space sorting algorithms. So maybe this is just maybe this is that, right, or whatever. But yeah, so for space, you're definitely going to create O of n because you have to create this array. But you could say it's O of constant extra space if this sorting algorithm is constant. Is constant space. Sorry, terrible explanation at the end, guys. Hope you have a beautiful day.